Hi everyone, welcome back to my video this morning. Today we are going to consider a topic called calculus of variations. And what this topic is talking about, it all comes under infinitesimal calculus, but it's a difference from the standard calculus we talk about, the calculus we normally study in our secondary school. This one here, calculus of variations. In standard calculus, for example, imagine you are given a curve and they want you to find the properties of that curve, whether it's a straight line, its points of inflection, that is, find its maximum, local maximum, global maximum, or minimum point. You find the properties of that curve, to say. But in calculus of variations, you are given the properties already, and then you go to find a curve that will fit in with those properties. So one example of that is a problem I have here. We're going to solve this problem. The problem reads: a lifeguard or a coast guard, somebody watching in the beach, people are swimming, you are a coast guard watching what is going around, make sure people are safe. So this is the kind of scenario. If you see somebody swimming and they're in trouble, you got to jump in to assist, to save them. So a lifeguard is on duty, standing 8 meters from the shoreline. 8 meters from the shoreline. Using a woman here. She sees a swimmer in trouble 40 meters further along the shoreline. In this case, it turns out that when taking the shortest possible time to reach the swimmer, the distance that she runs is equal to the distance that she swims. If her running speed is 4 times her swimming speed, how far from the shoreline is the swimmer? This is the question. Very interesting question. Here, the measures things here I need to explain a little bit. In this case, it turns out that when taking the shortest possible time to reach the swimmer, the distance that she runs is equal to the distance that she swims. Here, what this statement is saying here, the whole thing is a question anyway, but what just this statement here is saying, is talking about the distance. Because in solving these problems, we're going to apply 2 principles. One is a law, the other one is a principle. We're going to use Fermat's theorem, Fermat's principle, not a theorem. We call it Fermat's principle of least time. And Fermat, they call him Pierre de Fermat. He was a French mathematician. He reckoned that when light travels, a ray of light, when it travels from one medium to another medium, for example, from air to water, or from glass to water, whenever light does that, the speed it takes from one medium and the speed it takes to enter the other medium, the angle of entry and the angle of refraction, if you take those ratios, they are proportional to the distances traveled by the ray. This is physics, but we use it here to solve our problems. And in doing that, we also have to think of another law called Snell's law. Snell, his full name is Willibrord Snellius, is a Dutch astronomer and mathematician, Dutch Holland. And he helped, a lot to formulate the laws of refraction of light. He did a great job in that sense. So now let's see how we're gonna solve this problem. Yeah, I turn the board as usual. Now the question is at the back, so I'll be reading the question from here. The question says a lifeguard is on duty standing 8 meters from the shoreline. Let's say this is the shoreline. Yeah, this is the water here, and this guard is standing here. Let's call her Amina. Amina is standing here. She's 8 meters from the shoreline. This is 8 meters. It's a beach, yeah? So this is the water. All here is water. So she sees a swimmer. She sees a swimmer in trouble 40 meters further along the shoreline. So the swimmer is somewhere here. Somewhere here. Who was swimming? Let's say Hassan. Hassan was swimming. And Hassan is swimming 40 meters from the shoreline. Further, 40 meters. So Hassan distance here to here, 40 meters, right? In this case, it turns out that the shortest possible time to reach the swimmer. In this case, it turns out that when taking the shortest possible time to reach the swimmer, the distance that she runs to the distance that she swims is equal to the distance that she swims. All right, what they are trying to say here is that if you see somebody struggling here, somebody is swimming, maybe they're not good swimmers, struggling, and you want to help that person, but you are all the way here. So when we mention those two, one Snell's law and Fermat's principle of least time, because Fermat's principles of least time, what he's trying to say, a ray of light will always take the least time to leave one medium to enter into another medium. What that means least time, we can interpret it to be maybe the shortest amount of distance. That's what he's trying to say. So if Amina is here, she's trying to help Hassan, who is swimming all the way here, 40 meters from where Amina is standing. Yeah? Amina is standing 8 meters from the shoreline, but the distance from that shoreline to where Hassan is struggling is 40 meters. So where can Amina enter in order to help Hassan? Does she enter here? She runs here because she got to run here. This is a ground, yeah? This one here is a gravel. But here is water. All here is water. It's water. Here she got to swim. And we know you can run faster than you can swim. It's just natural. You know? If you put you to run, you're much, much faster than when you are swimming in the water. So what they want us to do here, what's Fermat's principle of least time means in this question, since you have the ability to run faster than the ability for you to swim, so it's better Amina runs as much distance on the ground as possible and have less distance to swim. That is where that principles come in. Fermat's Fermat's principle of least time. That is where it comes in. What about if Amina runs all the way here and then here? Because at a certain point, she got to enter in the water to save this guy, Hassan. But she wants to run a very long distance and leaves a short distance to swim. That is what we are trying to do here. That's the nature of the question. So since we don't know that point where she's going to enter the water, we don't know the point where Amina is going to enter the water. We'll assume now she enters the water here. If her speed of running was the same as her speed of swimming, we can just draw a straight line. Direct. This one is gone. Okay. We can just draw a straight line because that is the shortest distance between 2 points. It's a straight line. So if her speed of running was the same as her speed of swimming, then we can just connect these 2 points with a straight line. But that is not the case. That is not the case. If her running speed, here the question says her running speed is 4 times her swimming speed. Running speed is 4 times her swimming speed. See that? Her running speed is 4 times her swimming speed. So she can run 4 times faster than her swimming speed. If the 2 speeds were equal, then we can just draw a straight line. Since the shortest distance between 2 points is a straight line. If you have 2 points, you want to find the shortest distance. It's not this one. You don't go like this. You go straight. That's the shortest distance. And that is what is Fermat's principle of least time is talking about when solving this kind of problems. Correct? So, let's go further. Now, what do we need? We say at certain point, Amina is going to enter the water. She has to enter the water. Then what is that point? We can draw a normal line here. Correct? And then, Hassan was here. Let it don't be a straight line, so let's make it like here. Correct. So if she enters with this angle, and she enters from the land with this angle, and when she enters the water with this angle we call R, enters with I from the air and in the water with angle R. Right? So, Snell's law tells us that the sine of I all over sine of R. Let's say this is the running speed. I is the running speed, angle of the running speed. So it's V of run all over speed of run all over speed V of swim. This is the ratio. This is Snell's law. It's already been proven in physics. They have proven it is a law already. We are just using it here. It's talking about the refraction of light, or the bending. We want to find what we are trying here to see here, how much this line is bending. Yeah, if you know the amount it is bending, it will help us to calculate what we are asked in this question here. How far is the shoreline? How far from the shoreline is the swimmer? How far is the shoreline? How far from the shoreline? How far from the shoreline is the swimmer? So this bending, the way this line bends, if Hassan was here, you see, it will keep on bending towards that side. So the amount it bends will help us to determine how far Hassan is from the shoreline. That's what the question is asking us to find. Okay, so now I believe we got everything we need. Yes. So what we need here now, let me make this diagram look tidy. Let me make it look tidy. Yeah, let me just redraw it. It's all the same thing, just to make it look tidy. Now we say Amina was here, and this is the shoreline, and from here to here we are given 8 meters, and Amina will have to enter the water at certain points. Put a line there. Sun is here. And this is angle, this is R, refraction. And what they want us to find is how far is Hassan from the shoreline. So this is what they want us to find. This distance they want us to find. This is shoreline. This is the Coast Guard. This is the swimmer. I don't need to write those words again. Yeah? So now, suppose, and we are told from here, from this distance to where Hassan is 40 meters. That's all we have. And we want this distance. Let's say this distance is H. Let's call it H. This distance here is the same as this from the shoreline. Yeah? We want H. H here. So we are given, let's say this distance here, this, let's call it D1, and we'll call this one distance D2. Okay? So we have from here to here as, let's say this is X. So that distance is X. Fine. So where do we go from here? Now, this is a diagram. We have transformed the whole question into this diagram. All that is left now is algebra. This way, question is done. We have a number here, we have a number here, we are asked to find this, we have unknowns here, and we have angles here, and we have distances given. Question is finished. Solved. It's just algebra now. So let's start. Let's start. After we've stated all those principles, Snell's law, Fermat's principle of least time, we understood now what those meant. So now let's start from here. You know, this angle here is the same as here. It's the same as this angle here. Why? Because this is an alternate angle from geometry. This line is alternate to this one, so they are both equal. Okay? So if you want to find the sine of this angle here, now we can say sine I, the sine of I is equals to opposite, which is x, all over hypotenuse. What is hypotenuse? Hypotenuse is d1. And here, let's do something here. We are given that from here to here, where Hassan is standing, is 40 meters. This whole length is 40 meters. 40 meters. But we want to consider this little triangle here. Yeah. This little triangle here. You know, it has an R here. Yeah. This is the angle here. And it has is R here, and the distance is D2. The hypotenuse is D2. But then we don't know this. We know the whole length is 40. We don't know this. So this one is going to be 40 minus x. Yeah? Because consider the shoreline, this whole line. Yeah? This whole line now, consider it to be 40 meters. And we have somewhere here, we'll say this is x. So what is going to be this? This is going to be then 40 minus x. This algebra. If you add all this together, you have x plus 40 minus x. What does that give you? This cancels this, so you get 40. So that is it. Yeah? So that's what you have here. Now, let's find the sine in order for us to apply Snell's law. Snell, S-N-E-L-L, Snell's law. That is Snell's law. You know, the angle, this angle here, if we say this is sine of R, is going to be opposite, which is 40 minus x, all over the hypotenuse, which is D2. Now we can apply Snell's law. Yeah? We can now apply Snell's law. So it says, sine of I, which is x over d1, okay, x over d1, sine of I, which is x all over d1, all over sine of R, which is 40 minus x, all over d2, is equal to v run over v swim, and we say the running speed is 4 times over her swimming speed. The running speed, v run, is over 4 times her swimming speed, so 4 over 1, which is 4 over 1. Yeah? All that is left is algebra. Problem is solved. Okay? Problem is solved. So we are assuming that D1 is equal to D2 because the question says it. she sees a swimmer 40 meters further along. In this case, it turns out that when taking the shortest time to reach the swimmer, the distance that she runs is equal to the distance that she swims. Yeah? The distance that she runs is equal to the distance that she swims. So that means D1 is equal to D2 from the question. So if that is the case, now this question will transform to x all over D1 divided by 40 minus x all over D1. Because D1 is equal to D2, we can say D2 equals to D2. So this will cancel, and it says all equals to 4. So now I will erase this since from this part. We now have x all over 40 minus x equals 4, which is x equals 4 multiplied by this will now go up, 40 minus x. So x now is equal to 4 times 4, 16. So 160 minus 4x. Now you have 5x equals 160. So if you divide both sides by 5, this will give you x equals 32 meters. So we now know this D1 or D2 is equals to 32 meters. Okay? This side understood? So I need space, yeah? Take it off, rub it off. Rub it off now. So, but the question we are asked to find is how far is Asan from the shoreline? How far is this man from the shoreline? So we are looking at H. This is what we need to find, this distance here. So how do we find that? It means we are looking at finding this. This is also H. It's H. Yeah? So for us to calculate what H is, we now know this. We know this is 40 minus x. We know this. Yeah? Here we say it was 40 minus x, yeah? 40 minus x. Because now we know d, but we don't know x. For us to find this distance h, we only know this. We know 40 minus x. But what is x? We don't know x. We've got to find x from here. So now we consider again this little triangle, which says now d, we know d is 32 meters. We know here is h, 8 meters. And we know this is x. We don't know what x is. Yeah? We can use Pythagoras theorem. Here is this h we want. We are looking at this triangle here. Our problem asks us to calculate h. But we know now d2, which is 32 meters. And this distance from here to here, we know is 40 minus x meters. Now we've got two unknowns. Yeah? With one equation. So it's not possible to find this distance here. So we need to know what x is. If we know what x is, we can easily calculate h. But we can get x from here. From this equation, from this triangle here. We know this, just one unknown. That's what we are trying to do here. So this is by applied Pythagoras theorem, which says that the hypotenuse, which is 32 squared, is equal to the sum of the other squares of the other two sides, which is h squared plus x squared. Hypotenuse, the longest side, is equal to the sum of the squares of the two remaining sides. So if we want to find our x, we'll bring it over here. So x squared is equal to now 32 squared minus 8 squared, which is, in the calculator, 32 squared, which is 1024 minus 8 squared is 64. $960. Yes, 960. And this is 32 or 64. Yes, 960. So what is the square root of 960? Square root of 960. Get 960 square is it's not a smooth 960 square root of 960 is 30 points. X now, find the square root, which is 30.9838. Let me stop there. Four significant figures. 98386.7. Let me stop there. Yeah? So now that's the value of X. We found X. So X now, here, we can say now 40 minus X, which is 30.983867. Now we can find this thing here. I think we are doing back the same thing. Let me just say minus 40. 40 minus 30.983867. So you get 9.0161. Yeah, so that is it. You got X for, you got this value down here now, is 9.0161. That is that value there. 40 minus X. That is what you get. Correct. But we need H. So H again, H squared is equals to, no. Again, we apply Pythagoras theorem here. The longest side, which is 32 squared hypotenuse, is equals to H squared plus 9.0161 squared. So I could have done something. I could have just taken the whole of this equation and fitting it here. It might cause confusion for some people. You see? So now you have 32 squared. Now you have H squared equals now 32 squared minus 9.0161 squared. So what is 32 squared? 32 squared again, 1024 minus 0.0161 squared. $81.29, and then H now is equals to 1024 minus 81.29, 942.7. So what is the square root now? What is now H? So that's now the square root of 942.7. 42.7 square root of 942.7, 30.7 meters. That's your final answer. Final answer. I think we can do it a lot better if we approach it this way. Let's approach it in a simple way. That's actually very interesting. Oh, now we need this H, yeah? But from here, we've already got like D1, which is 32 squared is equals to x squared plus 8 squared. So x squared is equals to 32 squared minus 8 squared. Let's leave it that way. That is the value of x squared. Now, from here, we need h. This is h we need to calculate. And h here, we know again, this is equation 1. 2 here, we can say d2 again, which is 32 squared, equals to h squared plus 40 minus x squared. Minus x squared. And then this will lead us to h squared plus 40 squared minus 80x plus x squared. But we know x squared is 32 squared minus 8 squared. So this is equal to 8 squared plus 40 squared minus 80. Still need x. Still need x. Still in x, so let's leave it as it was. Yeah, we leave it as it was. So you've seen the problem. We'll apply Fermat's principle of least time, apply Snell's law of refraction. Thank you for watching this video. Thanks a lot. See you. Bye bye.